David Smith here with yet one more flipped classroom math lesson. 3 tips before we start. First, you can adjust the playback speed faster or slower to suit your desire. Second, you can pause the video at any point to jot down questions or catch up with your notes. Third, you can turn on the captions so you can read my words on the screen. Today's lesson is on compound interest. And this is the kind of thing that you get with your bank account. So when you put money in your bank account, it earns interest. And the best kind is compound interest. And we're going to explore that by starting with comparing that compound interest to simple interest. Okay, so here we go. Check this out. Here's our definitions. Simple interest is an amount that's paid on your investment only. Okay, so if you put 10 grand in a bank account for 10 years and you get 5%, you're just going to get 5% on 10 grand each year for 10 years. So that's how that one works. Compound interest is a little bit better because it's interest that's paid on your invested amount and on the previously earned interest. So check this out. Here's how it works. In your first year, you would make whatever interest you make in that year. That money goes into your account. And now the interest you earn in the second year is earning interest on your original investment plus the interest that you earned during that first year. So that account, that investment's going to grow faster. So let's take a look and compare a couple of these, okay? So here we go. And we're going to treat this like a sequence. So that's why we're dealing with this in the sequence chapter, is that you really can think about your account as growing by increments, in this case, every year. So let's check this out. Here's our invested amount that we're starting with. So in the first year, we shovel $1,000 into our account, and this is what this part is saying, $1,000 invested at 5% per year. So at the beginning, both counts have 1,000. This one we're going to do simple interest, and this one we're going to do the compound interest, okay? And you'll see how this one increases faster. So, but they both start off with $1,000, and that's our first term in our sequence, $1,000. So let's take a look at this. So after 1 year at 5%, 5% of 1,000 is just going to be 1,000 times 0.05, which equals $50. So the amount in the account after 1 year is going to be 1,050. So pretty straightforward. Now it's going to be the same for this account. We have $1,000 at 5%, we're going to earn $50. So at the end of 1 year, this account will also have 1,050. Okay. Now, second year, this account is earning simple interest. So the second year, which is U3, remember U1 is kind of like the 0th year. U2 is after the first year. U3 is after the second year. It's just going to get another $50. So the amount in the account this time is going to be 1,050 plus 50, which is going to be 1,100. So yeah, it's growing. Now this account's going to have a little bit more because here's how this goes. We're going to have 1,050 plus 1,050 times 0.05. So notice how here's where we start. And here's the interest. So now we're earning 5% on 1,050. So go ahead and pull out your calculator and tell me what my total is going to be for that year. Okay, so if you got $1,102.50, you're right. Now, it's not a huge difference. This account only made $1,100. This account made $250 more, but it's significant. And if you think about it, what if you had $10,000 in there? And what if you put it in there for 30 years? The difference is going to be quite large at that point. Okay, so let's take a look at how we arrive at these using our formulas. Okay, so first off, arithmetic sequence. Simple interest, we just have a difference added every year. Because we started with 1,000, that's our U1, and then we're just adding $50 every year. So our nth term formula is UN equals 1,000 plus n minus 1 times 50. Our difference is 50. Here's our n minus 1, and we start with 1,000. So that is our nth term formula for this sequence, which is arithmetic. Now this sequence is geometric. It's going to grow faster and faster and faster. So what's our R for this? Our R is equal to 1.05. So we're going to have UN equals U1 times R to the n minus 1. Okay, so now let's plug that in with the information that we know. UN is going to be 1,000 times 1.05 to the n minus 1. So two scenarios. We've got our arithmetic sequence, which models simple interest perfectly. And then we've got our geometric sequence, and with our formula here, which is going to model compound interest. Okay, let's do another example. This time we're going to do a bunch of different things that are going to show you the different ways that the IB questions are going to lead you in and force you to kind of calculate it from different angles. Okay, so we're going to start with the basic one. We've got a situation with two dudes, Peter and Paul. They both have $2,000 to invest. Peter's bank gives him 3% interest per year, simple interest. Okay, that's cool. Paul's bank gives him 2.9%. It's a little less, but he gets compound interest, and it's compounded yearly. In future lessons, we'll talk about different compounding intervals, mostly quarterly and monthly. We'll see what happens when we compound more frequently. In real life, your bank compounds their interest daily. So that's the best result. That's what you get in life. Okay, so the first question we're going to answer is, how much in each account after 10 years? So remember, simple interest is a arithmetic sequence, and compound interest is a geometric sequence. So think for a minute, what you're going to need to do to get started with this problem. What do you need to find? So if you said, yeah, we need the common difference, you're right. It's not readily apparent here. We do need to calculate. So to find that common difference, we're just going to take our $2,000 and we're going to multiply it by 0.03, which is our 3%. And I happen to know that comes out to be 60. So that's our common difference. Okay? So now we know that it's going to add $60 every year. So U10 is going to equal 2,000 plus 10 minus 1 times 60 equals, and so, whoops, that's 2,000. Let's just squeeze that extra zero in there. So go ahead and pause the video and do that calc. Okay, so now that we know the difference, $60 every year, now we can calculate after 10 years. Now we need to think for a minute. U1 is year 0, okay? So year 10 is going to be U11. So U11 is going to equal 2,000 plus 11 minus 1 times 60. Now I know 11 minus 1 is 10, times 60 is 600, so we're just going to have 2,600 in the account. So not bad. All right, now let's take a look at Paul. Now pause the video and see if you can do the same calc for Paul. Now remember, we don't have a common difference because it's a geometric sequence, so you've got to find your R, okay? Okay, I did your plug-in step. U11, which is at the end of 10 years, we're going to have $2,000 times our R, which is 1.029. Remember, our interest rate is 0.029. But to get a multiplier that's going to increase, we have to add 1 to that. So we have 1.029 to the 11 minus 1, which is the 10th power. So go ahead and key that in, see what you get. So check it out. Even though this is a lower interest rate with compound interest, we actually made more money. We made $61.85 more. Okay, so I don't know about you, but I'd rather have compound interest. All right, let's do a more complex problem. And this one really kind of is going to show you the power of the compound interest. So here's the interesting question. After how many years will each account have at least $5,000? So this is kind of like a race. How long does it take this account to get to 5,000? How long does it take this account to get to 5,000? And this is really going to show you some of the power of compound interest. So for the arithmetic sequence, we can solve this one entirely by algebra. 5,000. That's what we're shooting for. We're trying to get at least that. That's going to equal 2,000 times n minus, or plus, sorry, plus n minus 1 times 60. Right? That's our formula. We just plugged it in. We plugged in the result, and we need to know what term would give us that result. So go ahead and pause the video and see what you come up with on that. Okay, I'm just going to do the algebra. I'm first going to subtract 2,000 from each side. So now I have 3,000 equals, and let's do the distributive property here, equals 60n minus 60. Oops, there's an n there. 60n minus 60, add 60 to both sides. 3060 equals 60n. Divide through by 60, and you get n equals 51. N equals 51. So it takes 51 years for this account to go from our initial investment of 2,000 all the way to 5,000. So it's kind of a long time, but we are more than doubling. We're multiplying overall this by 2.5. So that's a substantial increase. If this was 100,000, geez, you'd have like 250,000 in there. So that's pretty good. Action. All right, I messed around a little bit, erased that. If you didn't get it into your notes, just review the video a little bit, get that into your notes. Let's go on. We're going to find out after how many years it takes for this compound interest account, slightly lower interest rate, but let's see how long it takes to get to 5,000. So your first step, figure out what the plug-in step is, what equation is going to help you find that. And if you remember from a previous exercise, we ended up using logs. So I put these two log equations here because we're going to need them in just a minute. So go ahead, pause the video, and figure out what your step is here. Okay, let's do that. So our target is 5,000. That's what we're shooting for. To get there, we take our 2,000 and we multiply it by our R, which is 1.029, and we don't know the years, so we just put our n there, okay? So that's our plug-in step. Now we can divide through by 2,000. 5,000 divided by 2,000 is just 2.5. So that gives us 2.5 equals 1.029 to the n. Now, whenever you have a variable or an unknown in your exponent, you know you need to use logs to find that. So we have an equation that's similar to this one. If a and b are known quantities and x is the unknown, then you can transform that to log base a of b. You can put that into calculator and it will spit out x. So in this case, here's our a to the x and our b. So now what we're going to do is we're going to do log of base a, which is 1.029, of our b, which is 2.5. That's going to equal our n. So go ahead and put that in your calculator and see what you get. So that spits out 32.05. So if you're answering this question strictly, it's going to take 33 years to get there. The interest won't be compounded to the end of the 33rd year, because at 32, it's going to be a little less than 5,000, because we need 32.05 years to get to 5,000. But it's not going to compound at 0.05 years. It's going to go all the way to 33 years. So that's 33 years. Now, if you look at your notes, or if you remember, this one was 51 years. So, pretty big difference. This one is almost 20 years longer to get to $5,000 with the same initial investment. Plus, this one's at actually a little bit lower interest rate. So if this was 3%, then this would be even smaller. And if you want to try something new, put in 3% and see what you get. In fact, I'm going to do that right now. Why don't you do that too? So at 3%, I get somewhere around 30.9. So that's going to be 31 years. So after 31 years, so that's even better. So that is 20 years quicker than this one. Plus, check it out, 0.1% of interest. It's not that much. It's a 10th percent, 0.001 shaves off 2 years of the time to get to $5,000. So this should be showing you the power of compound interest. Now that you've watched the video, take a moment to jot down extra notes or jot down some questions for our next class. You can also re-watch portions of the video that you didn't get the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.